Hello everyone, this is Dennis, and you are on the Den Electro channel. Today I will show you how to make a very simple but effective tester for Zener diodes and LEDs. The idea of creating this tester was suggested to me by one of the subscribers under the nickname Namatov M3774. Many thanks to him for this. The Zener diode tester will work from a cell phone charger, but it must be upgraded first. I will now tell you in detail how to do all this. To make it easier to understand what we will do today, we need to understand what a cell phone charging circuit looks like. The diagram is simplified, so don't mind that there are a bunch of parts missing. All chargers have a step-down transformer that converts high voltage to constant 5 volts. A transformer has two windings, primary and secondary. The secondary winding current is rectified by a diode and smoothed by a capacitor. The charging upgrade will look like this. First, we will wind another winding around the transformer. It will have 100 turns. The minus of both secondary windings will be common. Then we will add an FR107 diode and a 3.3 microfarad 400 volt capacitor. Its capacity can be changed from 1 to 10 microfarads. The voltage is also not critical. You can take about 100 volts. On the factory winding, 5 volts will remain as it was. And on the new winding, there will be 60 volts. This figure turned out in my case. Your voltage may be different. In order not to scare anyone with the flow of information, I told only half of the alteration. I'll tell you the rest when we make these changes. I will use the simplest charger, low power at 5 volts. It produces a current of 500 milliamps. It needs to be disassembled and the board removed. There are few parts on the board. There is still a lot of free space in the charging case. This is very good. Additional parts can easily fit there. Then you need to remove the transformer from the board. It's very easy to find and usually looks something like this. A black cube-shaped thing with duct tape wrapped around it. The transformer has 6 terminals. 4 of them are on the high voltage side, and 2 are on the low voltage side. On the high voltage side, very thin wires are soldered to the legs of the transformer. Therefore, when you pull out the transformer, be very careful. Make sure that any leg does not pull out of the transformer frame and does not remain on the board, otherwise the wire will break. To disassemble the transformer core, you need to remove the yellow electrical tape and immerse the transformer in boiling water for 5–10 minutes. The glue connecting the core halves should melt. Then, using a thin knife, the halves of the core are separated and removed. If the core splits into several parts, this is not a problem. They can be joined with glue. Now you need to take a close look at the transformer frame. You need to understand how the secondary winding is wound. Pay attention to how the wires come out from under the electrical tape. I assume that the wire on the right goes around the transformer frame from right to left. Then it comes out from the left side and is soldered to the left leg. Therefore, I will wind my secondary winding in exactly the same way as the previous one was wound. On another charge, the winding on the transformer was different. Here, presumably, the wire from the left leg goes to the right, and the wire from the right leg, on the contrary, goes to the left, causing them to overlap. Therefore, the new secondary winding must be wound in exactly the same way. The direction of the new secondary winding is very important. You also need to determine on the transformer where the positive terminal is and where the negative terminal is, since both windings will have a common minus. In fact, Minus this will be the beginning of my secondary winding. We look at the board. Find the plus and minus on the USB connector and trace which pin of the transformer they go to. The minus usually goes directly, and the plus can go either through an inductor or through a diode. Now I begin to wind the secondary winding. I use a thin wire because the current here will be very small. I solder the beginning of the wire to the first leg, where the minus is located. I bring the reins behind the frame on the left and bring them out to the right. This makes one turn. In the first layer, I manage to lay 45 turns. Then I add 2 layers of insulation using mylar tape. Here you can also use thin electrical tape or tape. I wind the remaining 55 turns onto the second layer. It is advisable to bring the end of the rein up. Then I do 2 layers of insulation again. Here it is no longer necessary, but without it the wire will unwind and it will look prettier. Then I insert the core halves into the frame and tie them tightly with tape. Later, after checking the functionality of the entire device, the halves of the core can be glued together again, but again, this is optional. A high voltage capacitor can be taken from the ballast of a fluorescent lamp. You can of course use capacitors with lower voltages, either 50 or 100. But the fact is that you never know what voltage you will get on the secondary winding. If, after switching on, it turns out to be larger than the capacitor is designed for, it may explode. Therefore, here it is better to play it safe and take a high voltage one. I will take the FR107 diode from the ballast of priceless lamps there. This pulsed high voltage diode can withstand 1000 volts and a current of 1 ampere. Then you need to turn on and check the design. I don't solder the transformer to the board, but run it on wires. I soldered 4 leads only on the high voltage side. I did not connect the secondary winding to 5 volts. But if your charging has feedback on the low voltage side, then the output to 5 volts must be soldered. I soldered a capacitor and a diode to the new winding. To make it easier to connect the board to mains voltage, I soldered 2 wires. During charging tests, voltage must be applied through the light bulb. I use a regular 60-watt light bulb, but it is advisable to take its power less, 40 watts. In case of any malfunction, the light will light up and prevent the charger from burning out. I apply mains voltage, and everything immediately starts working. A multimeter connected to the new secondary winding shows a voltage of 61 volts. Then I took 2 resistors and soldered them in series. The total resistance was approximately 5.5 kilo ohms. I will also need a digital voltmeter. It can operate at voltages from 5 to 40 volts. And the range of measured voltage is from 0 to 100. On the back of the board, it is marked where each wire is connected. Black and red for power. In this case, it is 5 volts. And the yellow one is marked with the letter V to the measured voltage. That is, to 60 volts. This wire can be called either a signal or a measuring wire. There is also a trim resistor on the board for more accurate voltage setting. A voltmeter is not the most ideal, but it will work for checking Zener diodes and LEDs. The trimmer resistor can be adjusted so that up to a voltage of about 10 volts it shows accurately. And after this value, it will slightly overestimate the readings. But the error is very small. The second phase of the conversion involves me adding a resistor and a voltmeter. The 5.5 kilo ohm resistor R1 is connected to the positive of the new secondary winding. A voltmeter is connected to the 5-volt winding with leads marked plus and minus. This will be the power supply for the voltmeter. And the voltmeter terminal marked V, where the signal wire is located, is connected after the resistor. Thus, the voltmeter will measure the voltage not after the secondary winding, but after the resistor. Adding new details to my diagram, I soldered 2 wires to the plus and minus of the capacitor. At the other end of these wires, a resistor was soldered to the positive wire. I ran 2 wires from the transformer to the board. Thanks to this, a voltage of 5 volts appeared on the board, and a voltmeter can be connected there. The holes on the board remain from the USB connector, which I previously removed. The yellow measuring wire is still hanging in the air. I turn my device back on. The LED voltmeter is working and showing zeros. And the multimeter now shows on my winding not 60 volts but 70. This happened because I connected an LED voltmeter to the secondary winding at 5 volts. It turned out to be a small load. To compensate for the voltage drop on the 5-volt line, the power supply began to work harder. This affected my winding. The tension on her increased. The yellow measuring wire is still hanging in the air. That's why the voltmeter shows zeros. It must be connected to the positive wire after the resistors. After connecting the wire, the voltage on the LED voltmeter began to be displayed. But for some reason, it dropped. Why did the voltage drop after connecting the measuring wire to the secondary winding of a 60-volt transformer? The fact is that every multimeter is inherently a load. Although its internal resistance is very large, when connecting its probes to some voltage, it still begins to consume current, albeit very small. It's the same with an LED voltmeter. When I connected it to the winding, it began to consume a lot of current. I then measured it. It was about 1.5 milliamps. Because of this, there was a voltage drop on the line. Now the device is fully operational. It can already be tested. This is a 3.9 volt Zener diode. And both voltmeters show a little more than 4 volts, almost correct. Resistor R1, or in my case, resistors must be selected in such a way that when positive and negative are closed, a current of about 10 milliamps flows through the resistors. Everyone who will assemble such a device will have different power supplies, different power, and different circuit technology. Even if you wind 100 turns like I did, the voltage at the output may still not be the same. Therefore, if you connect resistors of the same values as mine, the current can be either more or less. Why exactly 10 milliamps? The fact is that each Zener diode or LED has different characteristics. Some operate on a small current, while others operate on a large one. If you make the current very small, then passing through the Zener diodes, they simply will not work. They will not stabilize the voltage. And if you make the current very large, for example 20-30 milliamps, then this can negatively affect LEDs. Their operating current is usually very small. Therefore, a compromise has to be made here. Take a current at which the LEDs burned without harm to their health. and the Zener diodes stabilize the voltage according to their characteristics. Of course, there are more powerful Zener diodes and LEDs. This current of 10 milliamps may not be enough to determine their parameters. Because of this, the readings on the voltmeter will be incorrect. But this tester will still help determine at least approximately what voltage the Zener diode or powerful LED is at. Now that I know that the device works, it can be brought to an ideal state. I solder a 3.3 microfarad capacitor to the place where the USB connector was. And next to it I plug in a FR107 diode. I connect the power supply to the outlet again and see if there is voltage at the output. 60 volt is available. 5 volts are also available. Everything works great. I continue the assembly further. Now I will need long 3-core wires so that the voltage from the power supply reaches the voltmeter and probes. I will use cables from the mouse and keyboard. Each of them has just 4 wires. Then I put everything together and close the charging case. To prevent the wire from falling out, I fixed it inside with hot glue. It turned out pretty good. Next, we will need multimeter probes. I soldered resistors and wires to the tip of the red probe. I put them inside the dipstick and close it. I insert the wires between the LED indicator and the board. There are no parts inside, so the wires pass through very easily. There are small screw loops on the sides of the board. I tuck one of these loops into the back of the dipstick. It holds securely, but you can add a drop of glue if you wish. On the other side, in the same way, I attach the wires to the loop so that they do not pull out and solder them to the board. I covered the exposed areas with tape. Then you need to take a spool of thread and use a knife to make such a small case for the tester. Thin plastic can be cut easily with a utility knife. Then I put the plastic cylinder on the voltmeter. The finished device looks like this. The red voltmeter probe is the positive one and has 2 wires coming out of it. One of them is the negative probe, and the second is the power that comes from the cell phone charger. Both voltages come from charging, 5 volts and 60. Very easy to use. We plug the charger into the socket, take the probes in our hands, and apply them to the parts being tested. To understand how accurate my tester makes measurements, I will need a tester like this, purchased on AliExpress. Of course, its measurements are not the most accurate, but for amateur radio practice, it will do. The first will be a red 3mm LED. The factory tester shows a voltage drop of 1.91 volts. I am attaching a homemade tester. The voltage sometimes jumps and shows either 1.92 or 1.96. The measurements on both devices are almost identical. The next one will be the optocoupler PC817. The voltage drop across its LED is 1.15. My tester shows 1.12, 1.15. Next is the Schottky diode SR5100. The instrument readings are almost the same. green 5mm LED. The factory tester cannot detect this Zener diode at 11 volts, since its operating voltage is very low. It only shows the direct incidence on the semiconductor. Powerful 3-watt SMD LED. Here its voltage was also not determined, although I know that it is about 3 volts. Assembly with 2 Schottky diodes. Rectifier diode 14007. Here it shows exactly. Now let's look at SMD LEDs from an LED lamp. On one LED, the tester shows a voltage drop of almost 8 volts. The maximum voltage for these LEDs is 9 volts. They are called 2835 9-volt LEDs. The tester current is very small, and therefore the LED does not turn on at full power. If you connect 2 LEDs in series, the voltage doubles. 4 LEDs also pull and the voltage rises. Naturally, the entire plate does not light up since the voltage of my tester is less. But 6 LEDs are already working without problems. In such cases, the accuracy of voltage measurement is of little importance. The main thing is that it is possible to determine whether the LEDs are working or not. You can understand approximately what voltage the LED is designed for. Typically, their voltages are multiples of 3. SMD LEDs come in 3, 6, 9, and even 18 volts. The other plate shows a voltage of 8.15 volts. This means that 9-volt LEDs are also installed here. I'll take the third record. It shows 16 volts here. We can assume that these are 18-volt LEDs. 3 LEDs soldered in parallel also light up and show voltage. In the end, I decided to fill the sides of the tube with sealant. I first stuffed some paper in there so that the sealant wouldn't flood the entire board. This, of course, did not add any particular strength to the structure, but the wires on the right side stopped dangling. Yes, and I looked prettier. In order to be able to check many LEDs with this tester, the voltage of the secondary winding must be increased. For this, even more turns must be wound on the transformer. In this way, you can get at least 200, at least 300 volts to test the whole lamp. But keep in mind that when testing small LEDs, the current will be greater, and therefore some of them may burn out. That's all for today. Subscribe to my channel if you haven't already. Ask questions in the comments if something is unclear to someone, and everyone bye.